Hey guys, in this video we're going over projectile motions and constraints. And this lecture is relatively boring, so just bear with me. Here, if you have a ball over here and you throw it with the velocity of v, and you can vary the angles, like we want to find what is y of x. So basically, like, what does a trajectory looks like? So first, we separate it into Vx and Vy. So this one is equal to cosine, and V0y is equal to sine. And now we write the equations, which is y is equal to V0yt minus 1/2 gt squared. Well, I need to derive it first. Never mind. Okay, so first we're going to derive these equations. So the first one, we know that the definition of acceleration is dv over dt. So now if the acceleration is constant, then we have dv is equal to a dt. And take the integral from both sides. And from okay, so changing v is equal to a from 0 to t at. So which means that v final minus vi is equal to at, and v final is equal to vi plus at. And now we want to find out what is like displacement over time. So which we know that the velocity, like v final velocity, is a function of vi plus at. So basically it's a graph of vft can be drawn as this, because this slope is constant, which is a slope of a, and in this case we assume that a is positive, and if a is negative, it's the same case with negative slope. So basically, we know that the dx is equal to v t. So basically you take the integral both sides, and you can get that x is x. So changing x is equal to vit plus 1/2 at squared. Okay. And now, if we know that dv dt is also equal to d this over, okay, I'll prove it first. I proved it in the last video, and I don't know if you guys watched it. So this, using this chain rule, we can get this one is dv dx dt. Basically chain rule, and we assume that v is a function of x. And so this term is basically v, which is v dv dx. And we know that this, by the chain rule, this is equal to dx, which is 2v divided by 2 times dv dx. So basically, and this term is going to be this d 1/2 squared x. Now let me erase this part. And we assume the acceleration is constant, so we have this. And now if we move it to that side and take the integral, we have 1/2 v squared vi v final, and is equal to a changing x. So now we have v final squared minus vi squared is equal to 2a delta x. I think that's basically it for this kind of stuff. And from last video, we know that we can separate this v vector to x component and its y component. And similarly, we can get the equation to be this. And for the y direction is this, and x direction. Because there's no force, the only force is like perpendicular to the plane, which is y direction. And there's no force upon the like x direction, so dx dt is 0. So basically, v x is basically v final x throughout the time. Thus, let me erase it. Which is equal to v0 cosine. And we know that x is equal to v0 cosine t, and this is v0x. So t can be written as a function of x, which is very so t is equal to x divided by v0 cosine theta. And now if we plug into the equation over here, we can find the the function of yx, which is v0 sine theta times x, v0 cosine theta minus 1/2 g x squared of v0 squared cosine squared. So now we have the equation to be x tangent theta minus 1/2 g x squared v0 squared cosine. Because we know that sine plus cosine is equal to 1, and if we divide both sides by cosine, which gives cosine 1 plus 1, this term is 1, and plus tangent squared is equal to cosine. So basically this term is going to be 1 plus tangent, which is x tangent minus 1/2 g x squared v0 squared 1 plus tangent squared. Okay, now we're going to take a look at the envelope. So the envelope basically describes like algebra graph over here. Like if you have the same velocity and you launch it at different angles, you'll get a different graph, which is similar to this. So the envelope basically covers all the like trajectory. Like here is the envelope that covers all the stuff over like all the points inside the like projectiles. And how do we find this? So the first way is to use quadratic equation. So basically, we can write this function as tangent. So basically, this function becomes like y minus x theta and plus g x squared v0 1 plus this function. So if we vary the value of theta and to a point where there's only one theta can be achieved, like only one theta can reach this point, then we can find the equation for the envelope. I know this sounds kind of confusing, and I think the second method explains better. We'll go over it pretty soon. So basically, this is equal to 0. So the goal is to want to find when there only one theta that satisfy condition. So basically, it means that like there's only one solution for this kind of stuff. So basically, for a quadratic equation, we know that if like this has has only one solution, then delta is equal to b squared minus 4ac is equal to 1. So basically, this is telling us that, okay, let me write it out and expand it more. G x squared b0 squared plus 1 half g x squared b0 squared minus theta is equal to 0. And where's b? Where's b? Here is a b. B squared x squared minus 4a. Which one's a? What's a? Let's see, this one's c. And which is 1y plus and now if you expand it out, you can find the equation for the envelope. Okay, now we're moving on to the second method where you can find the equation for the envelope, which I think was way better, or not necessarily easier, but it's more straightforward, you know. So this is equal to 0. This is basically describing all the curves, like all the curves. Basically, it's telling us that, or whatever. This can be written as the form of y minus x tangent plus 1 over 2 v0 squared plus this. So basically, if you have a certain x, okay, so x in this case can be treated as constant. You want to find the maximum of y. So how do you do this? You basically take the integral, you know? You just take the integral where dy d theta is equal to 0. So basically, you will find a like maximum point of the like theta x y graph where you can reach the y maximum. So basically, this point, the derivative of this is basically 0 for certain x value. So now, because this over here, so dy d theta is dy d tangent and d tangent d theta, and this is like a constant, or it's not relevant because this is going to be like I kind of forgot the formula above, but it's not relevant. The secant, yeah, and you will only reach 0 when it's like here, yeah. I forgot about this stuff. So basically, the only thing we need to care about is this term, because this term can be equal to 0, and this term it's just not really relevant. So now we take the dy d tangent is equal to x minus, wait, let me see, 1 half g squared v0 squared times 2 tangent y okay, this is equal to 0, this is correct. Tangent. Okay, yeah. Okay, I get it now. So basically you set it to 0, so you can find the value of tangent. So now you have like divided by x, 1 is equal to 1 over 2 g0 squared, and there's a 2 over here, just basically erase this stuff, and times theta, times 10 over here. Cancel. So now tangent is basically v0 squared over g. And now if you plug in the value of tangent back to here, you can get a function to be v0, and this x minus this v0 squared. This is pretty cool. It's really cool, and I think this method is the superior one. This is better. Okay, let me erase this stuff. And now, going to the fourth question, is like launching at a like leveled. I forgot what it's called. Level of plane, maybe. Like you basically, here's a phi and here's theta. Or just change it. This was better. You can vary theta. And you want to find the maximum. So how what is the maximum it can travel on the plane? Like here is the maximum? I don't know. And here is the maximum? Maybe. It's kinda like this. And for this type of question, we have a trick over here. So basically, if you rotate this, graph to here, the problem is basically the same, you know? The problem is basically the same. You can't see any difference, you know? It just converted to the problem of like you throw a rock at this angle and gravity is pointing this-ward. So now using geometry, and this one is 90 degree, and these two angles are 90 degree. So basically, this angle is phi. So the x component is basically like, let me see. X is v0x sine theta t plus 1/2 g and cosine and sine, never mind, t squared. And y is what I'm doing here. V0 cosine. Oh my god, I'm messing up what I'm doing. And basically you have like, and this one's minus. I have g, and this one's cosine t squared. And now let me see. So basically you can solve for the function of t over here, which is, let me solve it. This one is 0 if you move it to that side. So basically using the quadratic equation, you can find x is basically v0 cosine theta plus minus, and we don't want minus because we know that x is positive. V0 squared cosine squared minus 4 g sine phi and times plus plus x squared actually yes, that's correct, and divide by 2a, which is g sine this. So basically you have x is equal to this plus v0 cosine plus 2g sine psi x. This one's t. What I'm doing? X d g sine. And you can plug into this equation. You basically get the function of y is going to be v0 sine, and times this stuff. This is hell. And minus this. Whatever. And now you're kinda dead. So you basically oh my god, I did this question wrong. What I'm doing. Oh my god, I did this. Never mind, you need to find the function of God. What is this question? Yeah. I'll go over it in the next video. We're moving on. Okay, moving on to constraint. So for the constraint of 2 points, and basically it's a rod over here with length of L. And if you set up the coordinate system as this one's x1, y1, and x2, y2. So basically the length is going to be this using the Pythagorean theorem. And if you take the dt over to both sides, you can get 2 x2 minus x1 x2 dt minus dx1 dt plus 2 y2 minus y1 d y2 dt minus dy1 dt is equal to 0 because this length doesn't change over time. And now you basically can see that the vector of this length is basically x2 minus x1 and y2 minus y1. And you can see that if it times the vector of this and times dx2 dt, dx1 dt, and y2 dt, and dy1 dt, as this is going to be 0. So basically, it is saying that like the difference in velocity in the direction of the L is going to be 0. So if you have a velocity over here, and here's a velocity of the other object on the rod, this is basically meaning that the difference of velocity in the direction of this is 0. So, and now you separate the velocity to like perpendicular to the rod and parallel to the rod. basically the velocity of this is equal to this. Okay, this one is actually really important, and you should know this. And moving on to planes. So the constraint of plane is that no velocity perpendicular to the plane, and velocity or velocity must be parallel to the plane. So basically, you can't have velocity like here. You can't have it. If you have the velocity of this is going to be really weird. So it basically means that it will like in the next second it will like go into the plane, which is really weird. So no, you can't have a component of v that is perpendicular to the plane, or else it will go into the plane, which is really weird. So all velocity must be like pointing in the direction that is parallel to the plane. And for this kind of stuff, and if you learn gradient, and here's a function of the plane. So basically, the gradient dot v is basically 0, meaning that like it must stay on the plane. Or this, or the velocity of the bar that stays on the plane must be parallel to the point it touches. Yeah, basically. Okay, we're going over the classic examples. So the first one, this one's really tricky, really tricky. I'm going over the crack symbol here, and you can pause it if you want to do this. So here's a real velocity over here, and we want to separate into the perpendicular to the rod or the string, and parallel to the string. And now we have this velocity is going, as the velocity that is parallel to the plane is going to be v theta, and divided by cosine. We know the constraint of the rod that the velocity that is perpendicular to the rod is going to be the same. So basically you have v0 cosine is going to be v, so v0 is going to be v cosine. And many students, for the first time, including me, will separate it into this, which is, if you have an object over here, you separate into this. So this way will lead the answer to be let me see, this one cosine. Oh my god. V cosine is v, and v, this is going to be this. And in this case, we assume that the real velocity is going to be a cosine, which is wrong. We can't do this because there's no constraint. It is not the right stuff, because the resultant of all the velocities point this-ward, so meaning that the boat will fly in this direction. So the curve is gonna be this, which is not correct. So in conclusion, for constraint problems, separate to perpendicular and parallel to the string or rod. And now we're going to take a look at the second classic example. This one is also kind of tricky. So you separate it into the direction that is like perpendicular and parallel, and using, you can have this and 90 degrees over here, so this is theta. So basically v1 times sine is going to be v2. Wait, really? Wait. Yeah, cosine. v2 cosine. So v2 is basically v1 tangent theta. Okay, we have a hard problem over here. Last stuff we're going to talk about today. So this one's kind of hard. So there's a cannon over here, and it shoots it shoots something which has constant velocity of v0, and we want to find out the minimum velocity it can or like you're able to vary the angles and want to find the v0 that can pass a wall, the v0 minimum. And how do we do this problem is that we set the equation first. So we know that this one is basically a delta y is equal to v0y t minus this. And the second equation is basically saying that this, so v0 cosine t and this height, so v0 cosine t is going to be tangent 30 degree, and if you move it to that side you can get this. And now from the second equation, we can get t is equal to this. And now if we substitute t back to the equation of h, we can get this equation, and if we cross out and divide it, we have the equation of this now. So we can rewrite and get the equation of v0 as a function of theta, and we can find v minimum by using this. So basically the derivative of v0 is going to be 0. And now we have the equation, like similar case over here. So this chain rule is going to be this. And this term is basically irrelevant. So basically we want to find where this is going to be 0. And now if we take the derivative, and we know that this stuff is just a constant and it's quite irrelevant. And now we just want to find the minimum of this. So basically if you take the d theta and we talk about it, it's just basically d10. And we have these terms over here. And there's secant squared. So if we set this stuff is to 0, we can get the equation of this. Basically, if you solve, and you can get theta to be 60 degree. And if you plug into the equation over here, you can get v0 minimum is going to be square root of 3gh. Okay, we're done with this lecture.